Hey, can a pair of pendulums help us visualize quantum physics? When these two pendulums are connected by a spring, their motion produces a striking exchange of energy and a useful model for understanding how interacting quantum systems behave. The apparatus consists of two identical pendulums, each with a 100-gram weight. A weak spring connects them, while a data harvest light gate records the motion as a silver interrupt flag passes through its beam. We can begin with a single pendulum. Its period depends on its length. Increasing the length increases the time taken for each oscillation. For small angles, the period is proportional to the square root of the pendulum's length. Now the spring is attached and only one pendulum is displaced. At first, almost all the visible energy is in this pendulum, but the spring applies a changing force to its neighbour, gradually transferring energy across the system. As the first pendulum slows down, the second begins to swing more strongly. Eventually, the second reaches its greatest amplitude, while the first becomes almost stationary. The process then reverses, creating a repeating exchange known as a beat pattern. This motion is produced by the combination or superposition of two normal modes. In the symmetric mode, both pendulums move together. In the antisymmetric mode, they move in opposite directions. The small difference between their frequencies creates the observed energy exchange. The light gate removes the difficulty of timing the motion by eye. In EasySense, a time at A timing experiment records each passage of the interrupt flag. As a pendulum slows, it spends longer inside the beam, helping us follow the changing motion and measure the beat period. The coupling strength can be changed by moving the spring further from the pivot. This gives the spring greater leverage, so energy transfers more quickly and the beat period becomes shorter. The expected relationship is approximately inverse square. The pendulums remain entirely classical, but their equations resemble those of an interacting two-state quantum system. Their normal modes are analogous to combined quantum states, while the oscillating motion resembles the transfer of probability amplitude between coupled states. The same mathematical ideas help describe molecular vibrations, electrical circuits, structural resonance, and coupled qubits in quantum computers. With two pendulums, a spring and a light gate, we can make the behavior of coupled systems visible, measurable, and much easier to understand. Thanks for watching. Remember to subscribe to our channel and download your free worksheet from the Practical Explorer tool at www.data-harvest.co.uk.